Hi everyone, my name is Nityan Raja. My matrix number is CE190043, and today I would like to present about activity 1, which is the series resistive and inductive load circuits. So as you can see, figure 8.11 shows a circuit with resistive and inductive load in series. The AC voltmeter is connected in parallel with the RL load, and the AC ammeter is connected in series with the RL load. So let's look into the procedure. So according to figure 8.11, the circuit has been simulated using 210 ohm of resistor and 0.4 Henry inductor in series as the load. The input supply is set to 10 VAC and 50 Hz for the frequency. The values of current and voltage had been simulated and recorded respectively using AC ammeter and AC voltmeter in table 8.1. The value of load had been changed according to the values given in table 8.1, and the result were recorded. The simulated value and the calculated value is then compared. So let's look into calculation. So in order to find the resistive value of inductive load, this formula is used, which is 2 pi FL. So to find the impedance, we use square root of R square plus XL square is used, and in order to obtain the total current and the load voltage, Ohm's law had been used. So these are the formulas which has been used to obtain the calculated value for this activity 1. So let's proceed with the simulation. So this is the circuit based on figure 8.11. So let's look into the parameters. So for the AC supply, we have set the voltage to 10 times by the 1.414, which is the formula for this RMS value, which we need to use in this simulation. So for the resistor, we need to set this into 210 ohm, and for the inductor, the value is 0.4. So let's simulate this circuit, and let's look what happens next. So as you can see, we obtained the total value of 40.9 milliampere for this total current, and for the load voltage we have obtained 9.99. So which when we round off, it will become 10 volt. So let's look into the results. So this is the table 8.1 that we have talked about. So these are the load values that we need to simulate in order to complete this activity 1. So as you can see, these are the values based on calculation that we have obtained, and these are the simulation value that we have obtained by using this Proteus software. So what we can say about this experiment? So based on table 8.1, the calculated value and the simulated value for this circuit is same for the voltage and the current measurement. We can say that in a series circuit, the current is the same for all of the elements, and for voltage is the sum of voltage drop of the individual components in resistive unit. In a parallel circuit, the voltage is the same for all elements. The AC voltmeter is connected in parallel, so the voltage reading is the same with the AC supply and the sum of the voltage drop of the R and L combined. So let's look into activity 2, which is the parallel resistive inductive load circuits. So as you can see, figure 8.12 shows a circuit with resistive and inductive load in parallel. The AC voltmeter is connected in series with the circuit, and the AC voltmeter has been connected parallel with the RL load. So let's look into the procedure. The procedure is same as activity 1. In this case, the RL load is connected in parallel. So let's look into the calculation. So in order to find the resistive value of the inductive load, this formula is used, which is 2 pi FL. So to find the total impedance for the circuit, parallel resistance formula had been used in order to find this impedance value. So for total current and total load voltage, Ohm's law had been used. So let's straight go into the simulation. So these are the circuit that we have produced using the based on figure 8.12. So let's look into the parameters of this simulation. For the AC supply, we have used 58 for the frequency and the RMS value of 10 volt for this AC supply. So this is the resistive load and the inductive load, which are connected in parallel. The AC voltmeter also is connected in parallel with the RL load, and the AC ammeter is connected in series in this circuit. So let's simulate this circuit and obtain the values. So as you can see, we have obtained the total current of 92.6 milliampere, and the voltage which is 9.99 across this R and L load. So let's look into this result. So these are the load values that we have used for this simulation, and these are the calculated values that we have obtained using the formulas, and this is the simulation value that we have obtained using the Proteus software. So what we can say about this activity 2? So based on table 8.2, the calculated value and the simulated value for this circuit is approximately same for the voltage and current measurement if the decimal values are not accountable in the calculated value. We know that in parallel circuit, voltage is equal across all components in a parallel circuit. The total current in a circuit is equal to the sum of the individual branch current, and individual resistance diminish to equal a small total resistance rather than add to make the total as in series circuit. So since the resistor and inductor are connected in parallel, the input voltage is equal to output voltage, but the current flowing in resistor and inductor are different. So let's look into activity 3, which is the series resistive and capacitive load circuits. So figure 8.13 shows a circuit with resistive and capacitive load in series. The AC voltmeter is connected in parallel with the RC load, and AC ammeter is connected in series with the RC load. So let's we look into the procedure. The procedure is as same as activity 1. In this case, the inductive load is replaced with the capacitive load. So let's we look into the calculation. In order to find this resistive value of this capacitive load, the formula is used is 1 over 2 pi fc. So to find the total impedance, square root of r square plus xc square is used in order to obtain this impedance value, and for this total current and for the load voltage, Ohm's law is used. So let's we straight away proceed with the simulation. So this is the circuit that we have simulated using Proteus software for this activity 3. As you can see, this is a series circuit with a resistive and a capacitive load. The AC wattmeter is connected in parallel with the RC load, and the ammeter is connected in series in this circuit. So the resistance value has been set to 390 ohm, and the capacitor value will be set into 2 microfarad. So let's we simulate this value and see what are the values that we have obtained. Okay, the simulation is complete. So for this circuit, we have obtained the total current of 6.16 milliampere, and for the voltage we have obtained 9.99 volt across the RC load. So this is the result that we have obtained for this table 8.3. So these are the different loads that we have simulated using Proteus software, and these are the values that we have calculated using the formula. So these are the values that we have obtained during the simulation in the Proteus software. So what can we say about this? So based on the table 8.3, the calculated value and the simulated value for this circuit is same for the voltage and current measurement if the decimals values are not accountable in the calculated value. So we can say that in a series circuit, the current is the same for all the elements, and for voltage is the sum of voltage drops of the individual components in resistance unit. So in parallel circuit, the voltage is same for all elements. The AC voltmeter is connected in parallel, so the voltage reading is the same with the AC supply and the sum of the voltage drops of the R and C combined. So that's all from me now. So I would like to pass this presentation to my teammate. Thank you.
Assalamualaikum, my name is Nik Nurakilah. So we continue on activity 4. The activity 4 is the parallel resistive capacitive load circuit, the RC circuit. So we're gonna measure the ampere and voltage for this circuit. So first we're gonna have the EC voltage and the resistor and capacitor. And we're gonna put two multimeter here. One is for the ampere and one is for the voltage. And we connect it. Next, we set the parameter based on the value given here on this table. For parameter on AC voltage, AC is 10 volt and 50 Hz. And for the R is 39 ohms, and for the C is 2 microfarad. Then we run the circuit. So this is the result for the ampere is 18.672, and the result for voltage is 7.071. The voltage is voltage VRMS for this V peak because it's parallel. Okay, next is activity 5, the series RLC load circuit. So we use the same circuit, we just change the and from this value we have 390 ohms for resistor and 0.4 Henry for inductor and 2 microfarad for capacitor. And the VAC is 50 volt. So you can see we get our result here for the current and for the voltage. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Johari bin Zakaria, AE19009. I will present about the activity 6, which is the RLC parallel circuit. From this In the circuit, you can see this is the RLC parallel, the AC power supply, connect the AC ammeter, and this is resistor, capacitance inductor, which is connected in parallel, and the AC voltage is also connected in parallel. Then we need to test the first example is for 390 ohm and inductor 0.4 Henry, capacitor 2 microfarad. And we run the circuit. Then we can see the AC ammeter we get 386.944 milliampere, and the AC voltage is 50 volt. Then we get the result. Then we can fill in the table below. This is the video. So after that, we can test for the other RLC circuit, like 390 ohm and inductor 1.0 Henry, conductor capacitance 2 microfarad. Then we run the circuit. Again, the answer is for the AC meter 180.547 milliampere. AC voltage remains same, which is 50 volt. Then we fill in the table below 180.547 milliampere, and the voltage is 50 volt. Alright, that's all from me.